Let me introduce our speaker, who are jointly sponsored by ISTS. Craig Shue from Worcester Polytechnic, and prior to that was a scientist at Oak Ridge National Labs and got a PhD in Indiana. He's going to speak to us about some issues with networks and security and all kinds of cool things. So, Craig.
Thanks. Okay, so I'm Craig Shue. I'm going to be talking today about enterprise networks, both how to secure them and to learn a little bit more about what's going on. So the first thing I want to talk about is the organizational needs that people have. So when you're a network operator, one of the biggest problems that you have is actually understanding what's going on in your network. So sure, you might be able to see some network flows, but you might not know exactly why those flows are occurring. So how can you learn more about why these network packets are appearing on your network and whether it's something that's good or bad? The next is that while we want to know exactly what's going on in our network as defenders and operators, we don't necessarily want our adversaries to know what's going on. So we would actually like to deny them any ability to do reconnaissance and understand what's going on. As far as systems are, what kind of vulnerabilities exist, we would like to make it so that they don't even know what's happening. To do so, I'm going to talk a little bit about a technology called software-defined networking. So some of you may already be familiar with this. I'll give you the brief highlights if you're not to let you know how this technology works and how it can fit in. I'll then give you a little bit of an idea of the kind of background that organizations have and what threats they're facing, and then talk about two different technologies that I've fused together in some of my research. So, without much ado, the first thing is situational understanding. So if you think about a traditional network, you have hosts that want to be able to communicate with each other through some sort of switched path. So if I have some packet coming from the internet, I may send it through a router. It may be seen by an IDS and switched until it reaches a host. Anything that crosses my organizational boundary, I have some record of because it traverses my router and it traverses my defensive mechanisms. But what about traffic that doesn't cross that boundary? So let's say that I have traffic going from host 1 over to host 4. That never traverses my router, it never traverses my IDS, and as a network operator, I may never know that this packet is even there. So it's possible that one of my hosts will get compromised with malware, and I won't even know that it's spreading throughout my network. Okay? The same kind of thing can happen in other switches. So what actually caused these packets to occur? So when we say that, of course, there's some application on one of these machines that is emitting a packet, and that is why it's traversing the network. But why? Is it at the user's behest? Did the user click on some button saying, I want this network traffic to occur? Or is this something that's happening passively in the background? Is this perhaps malware trying to transmit information? So was it something that the user did? Was it something that the system administrator had running? What exactly is going on here? At the same time, attackers may compromise a host inside your network and then start trying to probe and find out what other systems exist. So they might send out multiple packets trying to infect additional machines, and you may have compromises spreading throughout your network without your knowledge. So that takes me to the topic of software-defined networking. So SDNs are an approach that are supposed to make it so that we have more control over our networking hardware. And some look at this and say, this is going to solve our access control problems for networking. That's not quite right, but I'll tell you where that mindset's coming from. So the first thing that you can do with an Ethernet switch is you can divide it into different layers. The first is going to be the data layer, the data plane. And this is actually going to be the high-speed hardware that is responsible for taking a packet into a particular port, looking it up in a table, and sending it out the appropriate port. And it's going to do that as fast as it can. So we need integrated circuits. We're going to need fancy hardware to be able to make that go quickly. The other portion is going to be the control plane. The control plane is responsible for populating the tables that the data plane is going to be consulting to figure out where to send the packet. So normally the control plane in a switch is going to be something like a learning switch. So it's going to be saying, as I receive packets and they come in through a particular port, I'm going to look at the source port associated with that packet, and then I'm going to say, when I need to send it to this MAC address, I send it out that port, the one that it just came in on. So that's a relatively simple one. Other switches can be managed and have specific functionality, and you can actually essentially configure your switches to have different ports do different things and things like that. So all of that would be in the control plane. The difficulty with this is that the control planes are typically proprietary. Right? So Cisco is going to have their control plane for their hardware. Juniper is going to have their own control planes. That's how it works. And they give you software that you can use to configure that device, but that's it. And computer scientists of the world are going, okay, they get to set all the terms and tell me how I'm going to use my hardware. I'm not okay with that. So instead, what we've looked at with OpenFlow is a technology that actually lets you program the control plane for your switches. So you can have a traditional control plane that does that learning switch mode. That's fine. But you can also have something that will go and talk to another computer to learn how to populate these tables. So for example, my laptop could actually be a network control unit and simply tell a bunch of these fancy switches, here's what should be going into your tables. When you see a packet that looks like this, send it out that particular interface. This can be really powerful. So as an example, one of the things that you can do is start actually specifying each of the different fields in the network packet that you want to match on and to make rules against. So for those of you who've used IP tables and started specifying a lot of this, this is going to be very familiar. You can say, if it comes from this MAC address going to this MAC address, and this IP address to this IP address, and these TCP ports and UDP ports, then do something. And that action might be forward the packet out port number 4. Or it might be drop the packet because it's actually something malicious. But you can actually program the switch and configure all of these things. You also have the ability to start using wildcards. So maybe you only care about matching the destination IP address and saying this IP address therefore goes out this particular port. And you're starting to look a little bit more like a regular switch that's doing some sort of layer 3 routing. Okay? You can start doing prefixes, and you can start aggregating things by putting in wildcards. Okay, so I've told you that this power exists. What does it actually look like when you have hosts communicating? So let's say that we have 3 OpenFlow switches, and we have a controller in our network. And we have the first host sending a packet over to the other host. When that reaches the switch's current data plane is empty. It has no idea how to forward this packet. So what it's going to do is go and contact the controller and say, hey, how am I actually supposed to do this packet? And so we'll ask a question, and the controller will consult some code running on the controller that will then tell it to populate that switch with a rule that matches this packet. Oh, this packet has this particular destination IP address. Here is a rule. Everything but the destination IP address is wildcarded, and it says go out this particular port. So I'm going to go ahead and tell you what that rule is. And I might even go and say, I know all the other switches that are going to be on the path to the destination, and proactively tell them what rule they need. So now that switch is going to consult its rules, and it's going to send the packets towards its destination. That's essentially how it works. Are there any questions about essentially OpenFlow? Okay, so this is a technique, and you may be looking at it going, if all of my switches ask these questions when they don't know what they're doing, I can make it so that my switches never know what they're doing. And if that happens, my controller will always be consulted every time it sees a network packet, and thus I can figure out what's happening in my network. Performance people in the room are probably going, yeah, that sounds awful. And we'll talk about how you deal with that issue. Okay, so next let's talk a little bit about some of the threats that organizations face. So many attacks that exist on an organizational network are user-level compromises. So many attacks that happen aren't actually compromising root. And so we can see an XKCD famously had a comic about this. They're like, if I secure my administrator password, no one's going to be able to modify my drivers or be able to manipulate my operating system, but they will have access to do everything under my user account, which happens to be everything I actually care about. And if you think about that from a defender standpoint, now realize from an attacker standpoint, you don't need root. You get all of the goodies by having a user-level compromise. So if we recognize that that's the situation, we can start saying, okay, can we start relying on the kernel to help us with things. Another thing, once we get a machine compromised, attackers are going to start using that as a pivot point. So let's say that I'm particularly malicious one day and I send Sean a phishing message. He's having a bad day and he just clicks on it and fine. Now I'm inside Dartmouth's network. And now I can start using his machine to start compromising a bunch of other machines. Hopefully, if I'm smart about it, I can do it through an Ethernet switched path and IT never sees me. Because I'm already inside the network, I don't have to worry about the firewalls and other defenses. So I'm now able to spread pretty well. So our threat model focuses on this idea of an adversary outside the organization that has good luck and is able to get a user-level compromise somewhere inside the network. What can we do then? Can we make it so that that compromise doesn't take over the entire network? Hopefully. So our threat model is going to have two pieces to it. We're going to first be trusting the operating system. Now that's an assumption that many researchers are a little bit hesitant about making. They're saying, it's software, it can also be compromised. If you can get a compromise in user space, why can't you also compromise the kernel? It's actually a little bit more challenging than that. Many machines have shared accounts. Linux boxes have lots of users on them. And we don't assume that all those users have root access because there's some defensive mechanisms there. Further, this assumption of a trusted operating system is one that we make all the time when we start talking about antivirus or host-based firewalls or any real host-based defenses rely on this notion of a trusted kernel. So while it makes us a little queasy, we're still going to just jump in with both feet on that. The other thing that we're going to be assuming is that we don't actually have an insider threat. This is not a case where we're saying that this is a user who has access to the network wiring closet and they can just take machines and start moving them around. We're going to be focusing on an adversary who's not physically present in the organization, and we're going to be assuming that our employees or people in the organization are actually working to the organization's benefit. And we'll talk a little bit about why we make that assumption in a bit. So with these assumptions, what we want to have is this centralized access control. We want to be able to say, here's what's allowed on the network and here's what's not. And we want to be able to essentially do this from a single place and be able to push out policy. Now, how it's actually implemented might involve distributed systems. We might avoid some of those concerns about bottlenecks and things like that. But logically, from an administrator standpoint, it seems centralized. So that's great. We want to be able to see everything. We essentially want network omniscience. We want to be able to control everything, being able to say this is allowed or this is denied. And we also want to know why this is happening. So that's the network catalysts component. What happened on that host to cause this traffic to be sent? So the first thing that we're going to be doing is essentially flow-based access control. So every new network connection, every TCP connection between one host to another host, we're going to label a flow. And a flow has 5 components that are specified: a source and destination IP address, a source and destination port, and a transport layer protocol telling us, is it TCP, is it UDP, is it something else? So those are going to be the fields that we're talking about identifying a particular flow on the network. Well, we could try to use OpenFlow to do this. It's a technology that exists. The only difficulty with OpenFlow is that it has some real scalability problems, which we'll talk a little bit about. And we're going to solve those. The other issue is that OpenFlow is only present on switches and routers. So you can't figure out why this is happening on a particular end host. So we're going to have to dig a little bit deeper into the end host to find out why this is happening. So I mentioned scalability concerns with OpenFlow. One of the things that OpenFlow can do is have all of these really fine-grained flows to match entries. But that's not typically how OpenFlow is actually being used. Typically what's happening is people are wildcarding all the fields except for destination fields. Like this is the destination IP address, and maybe I even put an IP prefix here. The reason that they do that is because OpenFlow must store every single one of those flow rules in the data plane. It has to be very fast for the packets to be able to match against it. And even top-end OpenFlow switches only have a capacity of about 97,000 flows. Okay, 97,000, that sounds like an awful lot. When you start dealing with a campus of this size, you're talking hundreds of millions of network flows a day. So during peak times, we're probably pushing way past that 97,000. Even worse, think of it from an adversary standpoint. If you know that there is networking hardware that exists on campus that has a limit of 97,000, won't you start trying to play with that? I mean, think about it. All right, so how many TCP connections can I have going at a time? Well, there's 65,000 TCP ports, so sure, I'll use 65,000 right there. How many UDP ports do I have? Again, another 65,000. Me, all by myself, have now been able to fill up the entire working set of a switch. Now, if I have multiple machines compromised, certainly I can do this without it being quite so obvious that I'm launching an attack on the switching infrastructure. So we really have problems here. If you start filling up the table with all of these flow-specific entries, you're going to cause other people's entries to be pushed out of the switch and have to constantly be reloaded. So you're essentially able to launch a denial of service attack on the entire network without much effort. I think your IT guys won't be pleased by that. All right, so if we can't do this with open flow hardware, we're going to need something else along the way. The other is a little bit of expense. So typically organizations like universities will refresh their switching hardware and their routers on a regular basis. And so maybe every 5 or 7 years, they'll be replacing the hardware. Fortunately, OpenFlow is becoming such a commodity that that's being integrated in new switches. But for organizations that don't do these refresh cycles, they can have very nice switches and routers that meet the bill that do not support OpenFlow. And until all of their switches do, they're not going to be able to use this for a security measure. And finally, you can't see anything on the host because it's deployed at a switch or router. So what we want to do is be able to switch it so that we're able to see all of this because the host tells us what's going on. So when we have a host that wants to communicate with another one on the network, the first thing it's going to go do is tell the network controller, here's what I want to do. May I do so? After it's authorized by the controller, it will then try to establish a connection to that other host and start sending traffic back and forth. But importantly, the destination isn't necessarily going to accept that traffic because it also has to go and ask permission to even receive the packet. So these requests and saying, I want to establish this connection, are also an opportunity for the host to tell the network what's going on. So the way we do this, the first round approach, I'm going to tell you how we originally proposed to do this, and then I'm going to tell you how we actually ended up revising it. So the first approach that we had was, why don't you just put every host in its own subnet, /32. Give it a route to its router, and it will send every single packet up through its router. By default, that's how it works. Great. Except that you've destroyed your network performance because now every packet's going up through the router. So how can we make it so that we can actually delegate flows and say, I'm not actually interested in seeing this at the router anymore. You're good to go. Go ahead and send the packets. So what we do is we create a way to de-elevate this traffic. And so this comes back to the analogy of mice and elephants. Has anyone heard the analogy of mice and elephants for network flows? Okay. So the idea with this is that there are an awful lot of network flows that exist when you're communicating that are very short-lived. So my laptop is probably trying right now to sync my email. It goes in and says, does Craig have any new email? No, he doesn't. All right, and then the flow is over. It's a very short-lived flow, and there are tons of these. Those are considered mice. An elephant flow is going to be one that has a lot of bandwidth going on. So you can think of a file server being backed up on a daily basis. It's going to be transmitting gigs and gigs of data. But there are actually relatively few of those flows going on at any time. So what you would like to be able to do is say that this is an elephant flow. It's going to have a lot of traffic going on, and it's one that I know and recognize. It's easier to keep track of just a few elephant flows and recognize whether they're secure, and de-elevate those out of your router. And for all the mice that don't last very long anyway, it's not such a big overhead if it goes up to a router. So the way we do this is that we have two sets of IP addresses for hosts. The first is going to be a persistent IP address, and that's going to be the one that has this default route up through the router, and it's in its micro subnet by itself. Whenever that host wants to talk to another host, and the controller says this is okay, what it's going to do is create a new IP address for that host, tell it to configure itself, and give a matching IP address to the other host it wants to talk to and says, the two of you can now talk directly, and here is a route that will let you do so. ARP for each other. Go ahead and send network packets. What's really nice about this is you can also do network address translation to stitch these things together and move traffic from the persistent IP address over to the ephemeral IP address as you need. So what does this actually look like? So the first line here, this blue line, is essentially the packet going from host 4 all the way up the most inefficient path ever through a network control device that has the ability to secure the traffic and control it. So what happens is that controller will say, you're now authorized to communicate directly with this host. And so it sends the green line out to the two different hosts saying, here is your new configuration. You should talk to this host directly. Here's your IP address. Here's the other person's IP address. And here are some translation rules that will stitch the connection together. You were originally sending on this IP address and these ports. Now you're sending on these ones. If you send it to both of them symmetrically, you can stitch together to the translation. And finally, the last rule is do not accept any traffic on this temporary IP address unless it's from the person I specifically said is allowed to use it. Okay, fine. We now configure the hosts that way. And what happens is they start taking the red line communication. They just go through the switching infrastructure, and you actually have the most efficient path available for that communication at this point. Relatively simple. And yet it gives you all of the network control that we've been talking about. So you have the ability to see all the flows that are happening on your network, even if they're hosts that are adjacent in your switching infrastructure. You're able to control them at both points, saying whether or not you want to allow or deny this. And you didn't have to change any of your infrastructure. You didn't have to replace a single network switch. You didn't have to place a router because that didn't change. The only thing we did was install some software on your hosts. Okay? So what if you want to monitor communication? If you're saying, you know, good, bad, I can't really tell. Good traffic, go ahead and authorize. Bad traffic, block. But all that stuff in the middle that you need to triage, you can simply monitor all that traffic by telling the hosts, oh yes, your peer's IP address is actually the IDS that I've created for you. So all of your traffic is going to naturally flow through an intermediary that you control in your IT staff that's going to inspect the flows, try to figure out whether they're good or bad. You only need to install that IDS on flows where you don't know whether they're trustworthy or not. Okay, so that's pretty neat. You can make some optimizations as well. So if you're going, oh, Craig, you used network address translation and now I'm done with you. Don't judge me too harshly, all right? There are other ways that you can do this without having to change out the IP addresses. So some of you may know something called netfilter. Has anyone ever used netfilter in Linux? Okay, divert sockets in BSD? Okay, then this is going to be really cool for you. There is a way that you can tell the Linux kernel, you will have this packet and you are about to send it over to this destination. But I, as a user application, hereby exert the right to inspect that packet. You can do that. If you're root, you can do a whole lot of things. So you can insert a rule that says this packet that is queued in the kernel should come down through this application, and that application will tell you whether it's okay or not to send that packet. Great. So you write a user space application in C and Java. It doesn't really matter. And what you do is you're going to send a packet back to the kernel saying this packet is okay to send or it's not. In the meantime, you have the packet in front of you, and you can change it. So if you wanted to do network address translation, you can just change the IP addresses and then say, this packet's fine. I approve it. Cool stuff like that. So you can actually get all the features that we're talking about without having to do any of the IP address manipulation that we talked about. So that's great. And the networking people in the room are like, great, Craig, you have this cool trick. What can you do with it? what security properties can you actually guarantee? So the first is we can simply use the policy language that already exists. So Polyth is a language for being able to specify what network flows are allowed in the network and which are not. There's also a flow-based security language that other people have come up with to formally model what is actually allowed on the network. So you can write these policies, you can install them in your controller, and it will enforce them across the entire network without you being involved. Some examples of this. Because we're doing this in user space, we can actually say what application caused this packet to be created. So I told you about that little net filter trick that I can do to grab things from the kernel. We can ask it, the kernel, what application created this? What process ID is associated? What is the executable path of that process? Who's it running as? Is it root? Is it user? What group is it associated with? You can get all of that information. And when you're asking the network, can I send this packet? You can include all of that. The destination is going to do the same thing when it receives the packet. So now I can actually say, this packet was created at the source because Craig used Firefox to send the packet. Who's going to be receiving it? It turns out Apache on the destination is running as the Apache user is going to be receiving the packet. Do you approve or deny? Probably you're going to approve that. If you find out that malware.exe is requesting to send packets to this server and it's running something you don't know anything about, you might say no because it's very suspect, right? So you can actually start talking about those kinds of controls. So another case, and this might really irritate some of you, is what if you know a machine is compromised by a user? And they have basically got complete control over this machine, and you don't actually have the ability to shut the machine down and fix it. You have to just limp along for a while with that user in your machine knowing that it's compromised. How are you going to get by with that? With this approach, you can simply say, yeah, machine is compromised. And if I let it talk to the attacker, I'm going to be in real trouble here. But I can make it so that I know a machine that is vulnerable, it is compromised, can only talk to people that I specifically authorize. And I can write policies to that effect. So you can actually have mission continuance even in a degraded state when you've got a compromise in place. Server load balancing, oh, that one's trivial. Just change the IP address that it's talking to, even though it thinks it's talking to the same one. Great things happen. So you might be saying there's got to be a cost associated with it. Well, there is, and it's in performance. So what happens traditionally when you have hosts issuing a connect request, you'll see that it takes less than half a second for them to be able to initiate the connection process, do the TCP handshake, and close the process. It takes less than half a second in the same local area network. With our approach, it takes 20 milliseconds, not 20 seconds, 20 milliseconds, which is about the order of DNS requests. So the amount of time it takes to get an IP address for a host name takes about 20 milliseconds on average. We would be adding an additional 20 milliseconds. That's really fast, though. People generally can't perceive something that quick. So we're saying, that's an overhead there. Also, this was in Python. We can probably get a little faster than that. So we're not terribly concerned about the performance involved. The thing we are a little concerned about is, what is the scalability of this? I just said OpenFlow is not going to work. You don't get a scaling factor on it. If you have every host on the network doing hundreds of flows, you're dead in the water. So what is our performance as we scale up? Unchanged, which is good. So we're not seeing a fluctuation as we scale up the number of flows. We get relatively the same performance. So at this point, we've done all the flow-based access control. We're able to control everything that's happening on the network. Now let's talk a little bit about how we can get a little bit more knowledge about what the hosts are actually doing. Knowing that it's Firefox talking to Apache, that's okay. But I think we can do a little bit better than that. So the idea here is that we want to know, sure, what application is originating it. We would also like to know whether it's running as root, an administratively installed place. We'd like to know what path it's installed with. But I'd also like to know how often is the user interacting with it. And you can think of it this way. If I'm interacting with an application, I'm essentially endorsing that application. If I'm typing a document in my LaTeX editor and I'm just going away for a while, it's probably the fact that I trust my LaTeX editor that I'm spending so much of my time interacting with it. Right? If it's malware, one of the things that's probably going to happen is it's trying to be as stealthy as it possibly can, because it doesn't even want the user to know it's there, let alone writing something that engages the user and gets it to interact with you. All right? It's relatively easy to write a silent malware. It is a lot more difficult to write a malware that has all the functionality of iCal or your email client or something like that to fool you into interacting with it. So what we're going to do is say if users interact with something a lot, they probably trust it. And if they trust it, maybe that's something we should take into account when we do network access control. So what we're going to do is take a look at some examples. If we've got a web browser, you might see that a user's interacting with it. They're typing in a URL, they're clicking things, and they press a button, and they say, OK, go. And now I'm going to have network traffic associated with it. So that is probably an indication that the user wants this to happen. Another application is a remote access tool, sometimes called RATS. And the idea with this is that an attacker will install this on your machine, and they'll essentially be able to do control your mouse and your keyboard and have all of your network access. Essentially remote control of your machine, hence the name. So these tools typically run in the background. They have no visual indication with them, and the user never interacts with them because the goal is to make sure they don't know it's there. Because if they do, they might take it to Best Buy and reformat the thing, and the game is lost. So these stealthy malware would be different as far as their user interactions go. So what we want to do is take a graphical interface. So this is my crude drawing of the print dialog box from Chrome. All right, so we've got a graphical interface there. And what we want to do is when someone triggers a button, to automatically go through and say they clicked a button and figure out what the context of that is. So for example, if they click the print button here, I will go through, I'll figure out what process is associated with it, I'll timestamp it, and I'll start extracting the text and say the button text is the word print. The parent object of the print button is a dialog box, and all of its text elements are, and then I get a list of all the text that's associated with that. I can then go through and watch what that process does. If it forks a child and then executes something, like calling LPR, and that LPR command issues a network connection, I can fuse this together and say, the reason this network connection happened is because LPR triggered it. LPR triggered it because someone clicked the print button in this process over here. And I'm able to reconstruct the entire chain of events that caused this event to happen. So how do we go about doing that? The first thing that we instrument is actually the graphics toolkit, the library that is associated with creating windows and widgets. So if you've used Java Swing before, it's equivalent to that. GTK is a way of doing that in the Linux operating system to create an interface. So we already know what functions you use to create visual elements on the screen. We go through and instrument each of those, logging the text that that button or that particular window has associated with it, and we log all of this along with the widget hierarchy. So we can go through and say the word print is in this button is in this dialog box is in this one. So you can construct the entire relation of all of these elements. We log all of that, and then we tie it into the network connection. So how well does it work, and what are the performance overheads? Performance overheads are tiny. So we were talking about milliseconds before. Now we're talking about 90 microseconds to actually take the text from one of these functions and write it down, essentially. And we only have to do that when the text is created. So if you create a dialog box that you pop up the window for the user, and the user just starts mousing it around, dragging the window around, you only write the text once. So that 90 microseconds is imperceptible. It happens very infrequently for how long dialog boxes in Windows are sitting in front of the user for seconds on end. So this is really quite good on efficiency. The next question is, what is the efficacy? Does it work? The answer is yes. So there are some little sticky components to it. So some of you may see that when you press the Alt button on your computer, you'll see that it changes all the characters in the menu bar, and it underlines some of them, and it says _F means file. And if you press F, something will happen. If you get rid of those little accelerator things, you get perfect accuracy. String comes in, string goes out. Perfect matching. We tried this previously using OCR, optical character recognition, on screenshots. We got like 70% accuracy, and it took forever to actually extract the text. So we're very pleased that our instrumentation works pretty well. There is a problem with this. And that's because a graphics library exists in user space, and users can choose which graphics libraries they use. So we actually had to instrument X11 in the kernel to confirm that the graphics library is not lying to us. So we're having to match things. The graphics library is saying this text, we're looking at it in X11. We don't really know what application it is, but we can say this string matches and start getting some consistency results in a trusted space. So now, with all this work done, the network controller can now say exactly why traffic's originating on the network. We can say what application, we can say what buttons were pressed, and we can control it all. That's kind of nice. You can also start taking into account those temporary IP addresses and start moving machines around for attackers, making it so they don't even know how many hosts are on your network. That's kind of neat as well. So great. I've built this. It works. We've got a prototype for it. We've got some efficiency results. So what are the next things that we need? So this is kind of my help wanted slide. If any of this sounds interesting to you, I would be happy to talk to you about it. So one of the things is, what kind of policy do you put on the controllers? I'm telling you, you can bind to Firefox and this user and buttons being pressed and things like that. But how do you actually write the policy? What kind of algorithms are you going to go through to actually analyze these things systematically rather than just manually constructing all of this, which would be a real pain in the butt? How do you deal with the huge volumes of data that we're going to be producing? Because there's going to be a lot of it. Also, what kind of understanding can you get from the user, and is that useful? So I don't typically interact with human beings as my users. I build systems for them. I don't interview them. We would like to be able to understand what's causing users to do things, and if our profiling techniques would actually be useful in practice. Oh, and by the way, we're collecting an awful lot of data here. We're recording all of these interactions that users are having on their machines, and we're purporting them to a box off the network. So there are some privacy concerns associated with this. What are those? How can we minimize them? In certain circumstances, this isn't an issue. If you work for a government lab, every time you log in, you sign away all your rights to privacy, saying, oh, this all can be monitored on behalf of the federal government. It's very intimidating. And you waive all of those rights. That's a little bit different than when you start talking about employing this on a university's computer lab, for example, where users may not be willing to sign away rights to that extent. So how can you balance these concerns? So we built the system. It provides something called defense in depth. We aren't just securing things at a perimeter. We're now able to secure it throughout the network. We're able to understand why it's happening. We can defeat the adversary's knowledge of what's happening. And we also have lots of ways that we can extend the work if you're interested. So with that, are there any questions? Thank you. Yeah, you had one.
So what about things like bring your own device?
Right. So when you start talking about BYOD devices, I can't get you to install software on your hosts. Well, maybe. So at WPI, for example, one of the things that you have to do to connect to our wireless network is install an agent. on your device that will install certificates and set it up, everything. So you could actually have it so that if you're on the WPI network, the instrumentation's active, and if you're not on the network, it doesn't report anything. So that's one way you can go about it. Another way you could simply do it is by putting the host in its own VLAN. So you can actually segment something using traditional switches, putting it in a VLAN by itself and proxying all of its traffic. The performance implications aren't good for that, but at the same time, cell phones, how much performance do we really need? And so you could actually kind of argue that point.
So I had a follow-up.
Sure.
Sort of unrelated, though, but related to your work. So what if Chrome pushes out a silent update? Do your rules dynamically update to validate this new dialog that does this, or do you have to have some sysadmin go in and add a rule? Seems
Right.
like a lot of the burden is on the sysadmins to have some algorithm, like you said, and
Right.
performance level.
Right. So it depends on how finely scoped your policy is. If your policy is going to be saying, I need the dialog box to have the print in this position and it has to be related to this container and I need all of that, yeah, changes in the layout are going to really mess you up. If you're content with simply saying, did the word print appear on the screen when something was sent to the printer, then I might be okay with it. And so then that's going to be a little bit more flexible across updates, even if they start rearranging things. But yeah, as updates occur, you would need to be constantly updating the approach, hopefully in an automated way. And I think that's some of the harder work, and I'm punting on that completely. But if you'd like to help, I'm very interested. Yes?
So I didn't quite follow how the print would get associated to the LPR command. Is it just time-based? You see a print and there was a command issue.
Yeah.
So now if all the malware keeps tab for the clicks and it sends requests, then how do you?
Right. So if you were trying to do this from a malware standpoint, one way you might do this is by trying to create windows and dialog boxes that have the words that are going to be applied to a policy, and then have the same kind of chain of actions associated with it that would look like a legitimate application.
No, not if the malware does. It just captures the clicks passively and just takes chances and sends random traffic, whatever the text.
Oh, you want to start clickjacking and have an application that's not active stealing clicks and making it look like the application's active? Is that where you're going?
It doesn't have to make it look active. Just steal clicks from an active application.
Right. Okay. So you may be able to get your malware to be able to subscribe to mouse clicks and keyboard strokes and make it look like it is recreating this and it is interacting with the application. And there might be various ways of doing that. What my approach to that would be is simply say, the number of ways that you can do that are probably relatively limited. And if I can instrument each of those ways of being able to say this is someone doing something weird, it's much easier to distinguish that from arbitrary application access. So I would actually go after the way that people are bypassing my mechanism and saying how many legitimate users are going to try to bypass in that way. That makes sense? We can talk further if you'd like. Okay. Other questions? Yes?
So I'm wondering from a security standpoint, we're putting a lot of trust in this application. If I'm able to compromise this application, I don't even need to compromise the network anymore. Isn't that kind of dangerous?
Okay. So there are kind of 2 points to that question. The first is if I can compromise the network controller, I get all of this aggregate information from all these hosts, and I have complete control over the network, and we're doomed. And that's totally true. So it does make the controller a more attractive target. About as attractive as maybe a BGP router connecting Dartmouth to the greater internet, because it would be able to see all the network traffic. So you have to trust in some things on your network. This is concentrating a lot of it into a single logical box. That might be a concern for you, but it's not something that we don't already do. The second part of that is the actual application on the end hosts. And so that might be more where your question was, is now I've got this application, and it has to run as root in order to be able to collect all of this information. Is there any vulnerability I can exploit in these things, and it will now grant me root privileges to that machine that it's running on? Yeah, that's pretty scary. And you're going to need to make sure that these user applications are are pretty well written so that they don't have vulnerabilities in them. Fortunately, they're small. So the Python script that I mentioned, I think it's maybe 1,000, 1,500 lines of code. So it's actually something that you have some chance of actually manually going through and code reviewing and verifying and doing all the best software engineering practices to make sure it's not vulnerable, as opposed to arbitrary code running on a machine, which is very daunting. So yes, there is that risk. Hopefully with good manual inspection, you can mitigate it. Questions? Oh.
You were differentiating between, you were detecting background processes as malware. So how do you differentiate between good and bad background processes?
Yeah, so there's a lot of background processes on a computer, and how can you tell if this is actually something intentional versus something that's not? So one thing, if we talk about my email client, for example, it's constantly syncing in the background, and I'm not clicking buttons in it right now. I'm talking to you guys. So how can we distinguish that from actual malicious instantiations? We can find out that the user started the application. So at some point, I went in and clicked in and said, start mail, and it did. So the user did take some action for that application when it started. The other thing is, my mail client was installed by root. Like the IT staff put it on there for me. So it has a trusted origin from the beginning. So even though it's doing background processes, they're not necessarily suspect as a result. So you can start using techniques like that and being able to say it comes from this particular root controlled path to be able to say this is more trustworthy than not. But really what we're saying is we're pushing all of this information out to a network controller and letting it decide with arbitrary policy. Hopefully they're good policy engineers. Do you have a question?
Yeah, more of a comment.
Sure.
You know, I work in the enterprise space.
Yes.
And I see what the trend is to address kind of some of these end user stuff with the concerns around bringing in a device and all that.
Right.
Is taking the most critical end user systems and putting them in virtual desktop and using VDI.
Yep.
You know, so your system admins might have their personal laptop that they do some stuff on, but any system administration work, they're going into a VDI, going to virtual switching, and this seems like something that would align really well with that.
Right.
Where you have a very controlled, trusted workspace that, you know, you could create those kind of policies for, and then align that with the virtual switching.
Yeah.
You know, so that the policy controller is controlling the virtual switching. I think that's something that would be really neat.
Yeah, that kind of fits in with a little bit of my experience. So when I was working at the Oak Ridge National Laboratory, many of us wanted to be able to check our emails on our phones. And Oak Ridge said, we didn't buy that phone for you. That's a user-owned phone. We want no part of that. But what they ended up compromising to was giving us an application that would essentially do the VDI thing and let us pull up our email through essentially a window gateway into Oak Ridge rather than running the email on our phone because they didn't want any sensitive information remaining resident on our phone. So there are approaches like that that are compromises, and I think it does fit really well in those contexts. Yes?
So it sounded like Trojan horse programs may give you some problems because they are ones that users are interacting with a lot, but may also have some unintended functionality in the background.
Yes.
Is there something you can do with, say, maybe just behavior-based rules, saying, okay, even though this is a potentially a trusted process, it should only be able to do certain things, or?
Yeah, it all comes down to the policy in the end. So when you deal with Trojan horses, yes, you have to identify what the installation source is probably going to be one of the best guides for you. And then the amount of interaction could be led astray. That's going to be really up to policy. The other way you can think about this, some of you may know of like DLL injection attacks and things like that for Windows applications, for example. You can actually get code that's malicious to run inside the process hierarchy of another process. Whew, how do we deal with that? And again, I would say there are only so many ways you can inject a DLL. Why don't you instrument those paths and be able to detect that it's happening? And then throw your hands up in the air and say, well, Internet Explorer has an extra thread in it of unknown origins. Do we allow it to still talk on the network? And that's your call for your policy. Other questions?
Just following up on that, it seems like if your default policy is whitelist, then you have a nice log, but if your default policy is blacklist, you have a lot of frustrated users.
Yeah.
So that,
Yep. I am creating the tools. I'm empowering IT to do what they want. Maybe it's future work. Maybe it's work I don't want to do in the future. But yeah, so there's, you definitely get an audit trail of everything, and that's the easiest thing I can punt to. But as far as the access control decision goes, let's be honest, even if you've got really good policy writers, you're going to make the wrong call sometimes. But at least this is going to be able to say, I made the wrong call, the machine is infected, and now I can isolate it. And I can find all the people it ever talked to and find out if they're compromised, which is at least better than where we are. Anything else? All right. Thank you, everyone.